My objective today is to show you data on survival and mitigation strategies for the two viruses, so swine Deltacorona virus and porcine epidemic diarrhea virus. And mostly I got selected to be maybe the person to talk about this within the group, but I want to really point out that this is the conjunction of work of very bright people and very hardworking people in our collaboration with Dr. Coyal, Fernando San Pedro, Michaela Trudeau, Harsha Versma, and Katie Cottingham. So these are the people that have done very good work on this area. And I wanted to bring back to, well, what is feed a vehicle for diseases, whether feed can be a vehicle for diseases. And most of the time when we see feed, we think about, or we have thought about chemicals contaminating feed. For example, in the case of dioxins, pesticides, or hormones, or for example, in the cases of animal proteins that are, or adulteration, like in the case of melamine. So in many cases, feed has been looked at a source for potential contaminant. Less so has been seen as a source of diseases. And so part of my talk today is to review that and what have we learned in the case of the disease for PEDV and swine Deltacorona. I will not get too much deep into the two viruses and the differences. I think we have very good talk this morning from Dr. Saif, and all than say that PEDV is a disease and that affects very young pigs, causing diarrhea. So the source of the virus may not be directly to the piglet, but to the mother or to the herd where the young pigs are housed. PEDV entered in 2013 and spread very rapidly to many states within the United States. And that rapid spread was raised a lot of questions on, number one, how did it enter into the U.S. and how did it spread so fast, where many farms had strong, and it spread not only into the U.S., but also spread through other countries like Mexico, Dominican Republic, Colombia, and through Asia. So very rapid movement, very rapid transmission in a short period of time. Therefore, the feed transmission question came to raise, and if you were here last year during the Carlos Pilloan Disease Eradication Center workshop, you had the opportunity to listen to many of these presentations where veterinarians laid out how they have seen directly firsthand work to determine or to relate the transmission of porcine epidemic diarrhea virus in feed. The first case that was presented was the case in Canada, where in January, the first cases of PEDV appeared in Canada, and after epidemiological investigation, many other routes of transmission of the virus were ruled out or were seen as we have been doing enough work in those areas that we will not have significant transmission of the virus. However, they still seen lots of nursery pig diet that tested PCR positive to the virus. So it contained fragments or the genetic material of the virus within that feed. They collect that feed and conduct a bioassay. And a bioassay is simply taking that feed and feeding animals and looking at reproducing the disease. And actually, they did it in two ways. They either fed the straight one porcine origin ingredient, spray-dried plasma, or the feed. When they fed the pure source of plasma to those pigs, they were able to reproduce the disease. However, when they fed the feed, they got combined result. So on and on suggests that maybe the virus was there, or the virus was able to, the virus that was in that feed sample was able to colonize or infect the animals, but when it was fed in a regular diet, the results were mixed. So it brings back to the questions where if there was exposure, whether the animals will get infected. Further work later on also look at sources of spray-dried plasma, a spray-dried porcine plasma that was contained significant titers of porcine epidemic diarrhea virus. And in this case, this group was not able to reproduce the disease. However, the question was still open for where does the virus came from and how that was infecting animals and if it really was related to feed. From the cases of the Swine Vet Center, nursery farms were infected where the source sow farms were not infected. They saw also rule out other sources of transmission, such as internal trucking, and batches of feed were testing PCR positive. Since they remove, at the time they remove ingredients of porcine origin, they stopped seeing new cases of breaking in those nursery barns. So indicated to that group that potentially that was how the virus was being transmitted. And you will have here later Dr. Scott D. from the Pipestone Veterinary Clinic, and they designed a very innovative way of collecting or swiping feed bins and collecting that dust and being able to reproduce the virus out of the, or reproduce the disease out of the dust collected from the feed bins that were suspect to be infected. But in these cases, we do not know where the virus comes from geographical or infections, or is actually that comes from the feed mill. In this case, the National Pork Board did a call for proposals, and we worked in some of these proposals at the University of Minnesota. And I put this slide for you together to for you to wait and see many of the other results from other groups. But one of the challenges is, do we get a measurement to really determine whether the virus that is there, instead of just the genetic material, is the genetic material being able to infect animals? So if I test PCR positive a piece of feed or a sample of feed, would that be able to infect some animals? We were, and I will talk more about the risk analysis and of the transmission of the virus in ingredients of porcine origin, and finally interventions to that mitigate the concentration of virus within feed. So what is a risk analysis? And that was the first work that we did. On the risk analysis side, the OIE has several steps where we have hazard identification. In this case, that hazard will be porcine epidemic diarrhea virus. And then with a risk analysis can be conducted, or a risk assessment based on data, and that will follow to some management of that risk and some communication. So in that risk analysis, we focused our work on ingredients of porcine origin, so rendered products, spray-dried products, animal pet byproducts, or porcine solubles or ingredients of the extraction of heparin. We did not focus directly in that first attempt on ingredients of, say, vegetable origin, such as cereal grains or bean meals or microminerals. But in a later project, we focus on these ingredients. What we did is we gathered data from the literature review on the factors that inactivate these viruses. And with consulting with the experts and in modeling some of the virus inactivation data, we're able to come to conclusions of how much likely is the virus going to be transmitted, or is the virus going to be survived, some of the processes that these feed ingredients go through. For example, in the case of spray drying products, there will be the steps of sourcing the plasma that is used in spray drying, the process of spray drying itself, the process of storage and packaging, that on all these steps, there could be inactivation of the virus. So we were able, as I will show you a little bit later, to make some calculations. Rendering, we've observed that based on the data that we had on hand, that the rendering process itself has been designed to control pathogens in these animal byproducts. And for many years, renders have had, not only is the render itself a cooking procedure of high temperature, long duration of time, that the virus will not be able to sustain, but also that they have best management practices and HACCP plans that decrease the likelihood of cross-contamination within the plant. And animal or hydrolyzed proteins like peptones, we also saw that the high temperatures and duration of these conditions were harsh enough to completely inactivate the virus in the material. In these two cases, the major problem will be cross-contaminations, because they are obtaining a product, or they are obtaining an input to their plants that have likely high concentration of the virus. In this case, the concentration of the virus could be variable, but it's a much milder process. Even though it's a much milder process, it's a process that is not only counting one kill step or the spray drying step itself. Because spray drying is a complex process, we had to take two approaches. We did a mathematical modeling using data generated at the University of Minnesota, or we used mathematical model using data from virus that has been worked at other places in Spain. In either case, we observed that significant virus inactivation occurred during the process of spray drying. And I remember that this process of spray drying is a combination of heating at the spray drying process itself, but also storage. And you can think that when you heat a feed ingredient, it does not cool immediately and stop killing all the virus. It's actually a process that takes hours to cool off, and therefore killing of the virus or inactivation goes as long as the time goes. The next project that we work on was, what condition does it take to inactivate the virus? Because part of this is, well, we can look at each ingredient, each feed material, but ideally we would like to have a big picture where we see what temperatures, what humidities, and what conditions take to inactivate this virus. So, and you can think that within the most common feed processing methods, there are different combinations of heat and duration of that heat. For example, with pelleting, temperatures are mild temperatures with addition steam or humidity, and short periods of time or retention time at that temperatures. Extrusion may have variable temperatures, but milder or greater temperature. Spray drying is much complex process where temperature and duration of the heating depends not only on the type of spray dryer, but also the conditions that feed goes or that plasma goes into later on the processes. And rendering, where it's designed to have much greater temperatures with much longer heating times. So what was done? Was we took samples of feed ingredients, spray dried plasma, meat and bone meal, corn, soybean meal, distillers grains, and some of the ingredients that we use. We also combine complete feed with organics or inorganic sources of acids, and we mix these ingredients, and we mix the ingredients with virus. Then the virus was incubated, and we observed the cytopathic effect of the virus. Then the data were analyzed on using a log linear or a curvilinear model or a Weibull model. And these are ways to explain the effect of the virus inactivation over time. And you can think that this data could be very useful in terms of calculating time and inactivation temperatures over time. So therefore, these models, very briefly, without bothering you too much with the mathematics, you can think of that virus can be inactivated very rapidly, and if you apply a log linear model, you may be doing some overestimation or underestimation of the virus inactivation at times, where log linear or where the Weibull models that offers tails or shoulders into the able to calculate, then offer more or a better fit to the type of data. And this is an example of that of those calculations. All samples were paired with a control sample that have no or additives, and we can see that in the samples were either the control or the pair sample with the treatment, and we were able to calculate then how long does it take to inactivate 1 log reduction of that ingredient. So with this way, it helps us to, in using this and mathematical tools, can help us to interpret some more of what it takes to inactivate the virus depending on the time and the temperatures. For example, at lower temperature or 120 Celsius, we can see that it takes some time for the virus to be inactivated, and then you get a quicker inactivation. However, as you increase temperatures, the dynamics change where the virus starts to be almost linearly inactivated. So the effect of heat is not a linear effect, where depending on the temperatures you may have different curves of virus inactivation. Why is that? Well, we still need to investigate what dynamics happens to the virus, or what are the temperatures that the virus can withstand. You can think that maybe the virus can stand some initial increase in the temperature, or you can think that the energy that it takes to heat the material takes longer here, and here is much faster. So in either case, we cannot think that a linear relationship, or if somebody else have done a kill of virus at 90 C, then we are going to increase a number at 120 and think that we obtain the same virus inactivation. Within feed ingredients, that inactivation can be different too across the temperatures. So if we can see that ingredients, for example, like blood meal, had a much higher inactivation at higher temperatures, while other ingredients have very little virus inactivation at the higher temperatures. So it seems that matrix of the feed ingredient also is affecting how well this virus is inactivated within the matrix. And yes, the matrix seems to matter, and here are log virus reduction or the delta value in days, and remember that the delta is the time that will take to reduce the virus concentration by 1 log. So in complete feed, the number was 0.22, and meat meal, for example, was 10. So 10 days in that product to really decrease into 1 log. So the matrix seemed to be matter as an effect on how to inactivate the virus. We took also samples of nursery pig diet and mixed that pig diet with some organic acids. And organic acids has been used in the past as methods to inactivate salmonella in animal feed. So we posed the question, where can this inactivate also PEDV? And yes, we observed that in some cases, so 17 days was the time to 1 log inactivation in the control diet, and we see a decrease of that value with addition of some of these acidifying products. However, you can think of still almost 1 day, maybe too much, to really render a product that is going to a very important herd and with a high risk of this transmission of the virus. And the survival of these two viruses between PEDV and swine delta coronavirus seems to be different. So in this case, there is a comparison done by Katie Cottingham, where she compared PEDV and swine delta coronavirus. And it seems that the time for virus inactivation is much greater in PEDV as in swine delta coronavirus. More work, I think, needs to be done on this area to really explain these dynamics, but it could be part of what explains what is seen in the field, where porcine delta coronavirus was less of a problem than PEDV. So in summary, inactivation conditions differ between PEDV and swine delta coronavirus. Viruses are inactivated by combinations of organic acids with variable effectiveness, and models of virus inactivation suggest a non-linear inactivation conditions. The final word that I want to leave you is on variability on assay, or variability on the ways that we measure the inactivation of virus in these feed ingredients. And we think that when we see a lack of model feed, we can think that, well, maybe the kinetics of inactivation are different from what the models were developed, or we see a lack of feed of that model because the inactivation conditions or the data was variable. There can be experimental error, for example, variability in cell growth or variability in virus titers. However, most of the times the alternative will be to do a bioassay. And inherently, bioassays could be of low sensitivity, or in many cases, there's still the question whether how many replications do you have in a bioassay where you have a group of pigs maybe sharing the same environment.